How does this thing work?
Well, wow. Throng been this full before. And you are in for a real treat. So Professor Popescu from Bristol University is here to speak to us about an immensely profound topic. First of all, of course, you all know who Sandu is, but just in case, he's one of the handful of people, no kidding, is regarded as one of the founding fathers of the whole quantum information business. So he's a co-author on some of those original seminal papers that actually made a science out of quantum information. So, and then I've completely lost track how many prizes and awards he won, but the Dirac medal, oh my gosh, the Bell Prize, and so many like this. And one more thing, this is important. Sandu is one of a handful of people. He literally had to compete against 2.25 billion people to win this one. I'm not kidding. He had to compete against the entire Commonwealth of England to become a member of the Royal Society. And then you have to sign your name close to Sir Isaac Newton's and all the other luminaries that gave us that. Come on, that's amazing, Sandu. Anyway, so this topic he's speaking to us about is one of the most profound. I think I've been watching you and Yakir and Daniel bang your head against the wall on this for about 4 years, and he finally solved it this morning. So now let's find out what it is.
Wow, that's fresh.
Well, given the fact that it has been published, it cannot be so fresh. you may imagine. But yes, it's been in work for a long time. So the beginning are in my PhD thesis, and the paper that we cited there is from unpublished from my PhD thesis, but there is a sort of preprint from pre-quant PH era. So people ask me because it exists only in physical form. In any case, so I'm going to talk about conservation laws in quantum mechanics. Now, I think that I would like to take a step back and discuss what are conservation laws in general and why there is a problem in quantum mechanics. So, as you learn already in high school, we have some conservation laws, like conservation of energy, conservation of momentum, perhaps conservation of angular momentum. And the idea is that you may have, I don't know, a bunch of particles that interact. And suppose that you know that there are no external forces acting on them, only forces in between. So then you can say, look, even if I don't know anything more specific about this, I can tell a few things. I can tell that a quantity, which is the total momentum, is conserved. So as an example, if two people sit on chairs like this that can move and have equal mass and push each other, then they go with the same speed, but in different directions. So if you add the two speeds, you get 0. And that is independent on how fast, on how slow you push each other. So you can see that. Multiply by masses, and then you can do something even if their masses are not equal. That's conservation of momentum. So the idea is you start the experiment, and at the beginning, you measure the system and you compute that quantity, whatever that is. Then you let the experiment proceed. And at the end, you measure again the same quantity. And you find out that the number must be the same. And that is precisely what a conservation law means. Some of the quantities are additive, like the total momentum is sum of the momenta. There are other quantities that need not be additive. But that is the point. This is how we do conservation laws in classical physics. And then in every single case, you see that it starts with the one value and you end up with the same value. Now, if you go to quantum mechanics, the situation is far more complicated. Why is that? Well, because I may start a system in some state psi, but this state psi does not have a well-defined momentum. So I can, for example, if I'm interested in conservation momentum, I can look at the Fourier transform, and it is some superposition of different values of momentum. Okay. Then what can I do? Well, I can measure the momentum at the beginning to see what's going on. But if I do that, I have a problem because I modify the experiment. Okay, so imagine, for example, that I would have something where a particle is localized here, and there might exist other particles somewhere around. If I measure the momentum of this particle, being localized there, it means it is a superposition of different momentums, and it has a better defined position, so it has a large spreading momentum. But if I measure the momentum, I will put it in some eigenstate of that momentum. Now it may collide with this one, where originally it wouldn't. So, although I could measure, and I could measure the momentum of each particle separately, and compute the total momentum, and then look at the end of the day and see that it is the same, but it is no longer the experiment that I'm interested in. Okay, because by measuring, I denaturate the experiment. So what do people do? Well, there is a strategy that people employ, and the strategy is the following. First of all, I prepare a system, and I measure, say, the total momentum. I may get one value. I throw it away. I prepare it again, I measure, I may get another value. I throw it away. I prepare it a large number of cases, and then out of them, I would describe some probability of having a given total momentum, some distribution of this thing. I throw all of these away because they are not in the initial state that I want. Now I start again with them in the state psi that I want. I don't measure the momentum. I let it evolve, and I measure the momentum. So I start at some time t initial, and at t final, I measure the momentum. I may get different values. So I look, if this was initial, I look at the probability final of P total. And if the situation was without external forces, I may see that this probability distribution equals that probability distribution. So that is the thing that it is done. But what is important here, remember, I started with, say, 2 n cases. In n of them, I measure here. In n of them, I measure at that time. And all I look whether the probability of some value among this is the same as the probability distribution there. But it is not that I have 2 measurements on a single system. To say this system started with this and ended up with the same number. Okay. Now, this is not really specific to quantum mechanics. You may even think classically, that you may have a situation in which a system, but if you measure a quantity, you definitely disturb it. So then how do you know what will happen? That is the same idea. On some samples, you measure at the beginning, On other samples, you measure at the end, and you look only at the distribution. So overall, this means that what I have in quantum mechanics, so in quantum mechanics, I have a statistical conservation. Okay. Theoretically, what you don't need to measure. So as far as the theory is just concerned, you look at the wave function at time 0, t equals 0. You look at the wave function at t equal to final, and you look what is the problem, what is the distribution of the particular quantity that you are interested in the initial and the final. So whether or not there exists a conservation law, that depends on the Schrödinger evolution of this thing. But what it actually means in practice means this game, convoluted game of having 2n samples, some of them you measure at the beginning and find the distribution, some of them you measure at the end. You don't measure the same thing on the same particle to check that it is conservable. Okay, so the fact that the distributions don't change, that is something that follows from Schrödinger equation, and that is what is considered the conservation law in quantum mechanics. However, just because, in hindsight, just because we know that that is true and it's a consequence, it doesn't mean that it is the only consequence of conservation. People got so used that instead of thinking that this statistical view is one of the consequences, for example, of symmetries out of which we get the conservation, that this needs to be the only one. Okay? So it's taken as granted that this is all you can do. Okay? Now, we, on the other hand, realized, coming from a very, very convoluted way, using pre and post selection, weak values, and things like this, we came to an example that challenges but looks very unusual. Okay. So let me see what is that example. Now, many of you probably here know this super oscillatory function, but let me just remind. So if I look at something 1 plus alpha over 2 e to the I x over n plus 1 minus alpha over 2 e minus I x over n all to the power n. This is a function. You can look at it like a binomial, yes? A plus b to the power n, and you can expand this in the binomial thing. So this will be equal sum over k from 0 to n, and choose k, and then you have this term to the power k, that term to the power n minus k. So I have something 1 plus alpha over 2 to the power k, 1 minus alpha over 2 to the power n minus k. I'm reshuffling a little bit the thing, and I have here e to the I kx over n times e to the minus I n minus k x over n. Looking a little bit at these two integrals, two exponentials, would be good to bring them together. So all I have to do is, what will I have here? I have minus 2k x. So this is it. That is how this particular function looks when I decompose. Now, let me look here at the exponents. So these are the space frequencies, the K numbers. So, okay, K goes between 0 to N. So it means that this thing goes between -1 and 1. The wavelengths are exactly the, and it goes in steps of 1 over N. If I look at the reverse, if I look at the wavelength, I see that it contains only very long wavelengths. From 1 is just from 0 to 1. Good. So it is if I would think as Fourier transforms, the Fourier transforms are bandlimited. Now look, however, at the same thing around small x. What exactly is small x, I will tell you later. So then I can decompose this in first order approximation. 1 plus alpha over 2 times 1 plus ix over n plus 1 minus alpha over 2, 1 minus I x over n, all to the power n. If I do a little bit of arithmetic here, I have half times 1 plus half times 1, that is a 1. Half times ix over n, half times minus ix over n, they just cancel. Alpha over 2 times 1, minus alpha over 2 times 1 cancel, but the only term that remains here is plus I alpha x over n, all to the power n. Well, you know what this is when we take n very large. This goes to e to the I alpha x. So this is for x small. What exactly is x small? I want x to be small relative to n. So if you look very careful, this will go when x is, for example, something like square root of n. In fact, if you are looking more detailed, x should be something like n. So x would be something like n at half minus epsilon. Then this limit goes. But I never told you what alpha is. And it was never really important. Whatever alpha is here, this is band limited. So I can take alpha larger than 1, which means that I have a frequency here that is much higher than the frequency there, that every single thing there. Okay, what would this mean? For example, suppose I have something with very long wavelengths. I have something here, I have another one, I have another one. And you are used to the fact that if you have in your Fourier transform some maximum frequency, then the resolution, the smallest detail, the finest detail, is of the order of the shortest wavelength. Well, that is not the case, because if I take alpha larger than 1, the wavelengths would be like 1 over alpha in that region. So it means that I add these things, and as a result, I may have something that oscillates here extremely fast. You can then show that, as a matter of fact, outside this, it starts exploding. But you can have a region where the detail is much, much, much finer than the shortest wavelength. Okay? How many oscillations like this? Well, all I need to look. Well, if I will take an alpha here, then alpha x should be of this scale. But I may have many, many, many oscillations there. So I can have a very interesting function, one that after that, many years after that, we call super oscillations. Good. Good, so this is a piece of mathematics here. Now, out of this, we did some physics. How we arrived to this is an entire story. As I told you, we arrived to this particular thing, thinking at the flow of time in quantum mechanics and other things. I saw Lev there. He had a famous paper with Yakir, in which a spin half particle behaved as if the spin is 100, and so on. So it all started with that thing. But in any case, what we've done here was to use this function and apply it. And here it's an interesting story. So suppose I have this box. This box that its length is of order n. And then I put in this box this photon, for example, within this special function, or let's say even a non-relativistic particle. Okay, so this function psi of x, which up to normalization is this 1 plus alpha over 2 e I x over n plus 1 minus alpha over 2 e minus I x over n to the power n. The longest wavelength is, you know, if x goes from 0 to maybe pi or something like that, periodic. Okay. So I put here something, and I know for sure that all the frequencies are between 1, minus 1, and 1. Okay, or all the wavelengths are long wavelengths. However, here in this central region, it oscillates tremendously fast. So there it is as e to the I alpha x. And then whatever the function here may, in fact, it is a very interesting exercise to show that whenever you have such a phenomenon outside this region, the amplitude increases. It really must work like that. And it is an interesting issue here relating analyticity and all kinds of other things. Okay, so suppose I have this particle, and here is now the game. I open the box, and for example, I stick in a mirror. Okay. If it doesn't make you feel uncomfortable, mirror like that, like a dentist uses, you know, you just put it in, and if the photon is there and it is extracted, then I take the mirror out and I close the box. But I don't keep that mirror for a long time. I keep it for a period. Imagine if this is a photon, and if this is a length of roughly like square root of n here, I keep it for a time that is, you know, that is this square root of n divided by c. So that I collect only the photon if the photon is in this region. Now, if it is there it is like a monochromatic wave with this high frequency. So in that case, it will come out. I close the door and I can check, is it out? If it is out, really it is in this monochromatic thing, chopped by the fact that I'm not looking at an infinite long thing, so it will be, you know, have a little bit of tail. But the frequency is e to the I alpha x. That does not always happen. Sometimes the photon is in a superposition of being here or being there. It's a single photon in this box. So sometimes it comes out, sometimes it remains there. When it comes out with a very high frequency, much higher than it had at the beginning. Okay? So the question is, where did this energy come from? Well, it's very tempting to guess Well, it's quite simple. This photon did not have that energy to start with, but I had to interact with it. I had to open the door, I had to stick the mirror in. So probably doing this entire process, I gave the photon the high energy. Okay. Now, that seems a little dubious to start with, because opening the door is something that is done on the scale of time, something with depending on the length of this region, square root of n, has nothing to do with the scale alpha. And you may imagine, you put it in there, it's like you may think that you may kick the photon or whatever. Nothing tells you that you could give an alpha. Okay. But there is a bigger argument which tells me that it is not due to the fact that I open. Okay. So first, just to clean up the thing, you may say, well, this is a time-dependent Hamiltonian that includes opening, closing. You could, every problem that is time-dependent, you can transform it into a time-independent problem if you put a clock explicitly in it. So you may imagine a particle that crosses, and when it crosses by the box, it opens, extracts the photon, and goes down. It's simple to do a model like that. So then the question is, when the particle came out, did this opener that went there past here and may extract the photon, you would expect it loses exactly the energy. So at the beginning, the spectrum of energies, let me imagine I'm talking not even of a photon, but I'm talking about, say, photon. It is between 0 and this maximum value, let's say 1, as we had according to that function. But then I get it alpha. So at the beginning, the probability was here. At the end, I will get the photon out. Okay. So how is the energy of this guy? Well, you would expect this to see some change when it came from here to there, perhaps to drop down into that energy. The claim is that that is impossible. And here is the reason why that is impossible. You see, let me clean this thing up. Imagine that instead of this funny prepared state here, I had the same box, but I put in the same box a monochromatic photon at this high frequency. Okay, and I send this opener or extractor to come, open the box, to kick out the photon if it encounters there, and so on. Now you have a monochromatic photon, you stick in a mirror. If it comes out with the energy that it has. It's the same color that it was in there. But remember that I do this in a time that is shorter than this square root of n over c. So my interaction only samples a piece there. But in this region, well, I should have made here with the same frequency as there. So that is very, very high frequency. This one is identical to that. So if in this case, I know for sure that the opener or the extractor doesn't lose energy, because what it comes out precisely with what it had inside. If here the extractor would lose energy, because it should lose this difference of energy from 1 to alpha, then I would be able to find out how the wave function looks in a region very far from the x equals 0. So I would violate special relativity. That means that just because of this argument, that although I have an extractor coming here, I will look at the spectrum of this extractor immediately. It will have enough energy that may give that thing. Why? I will explain it immediately. But the extractor cannot give the energy to this photon. So what you thought naively, you thought the following thing. Look, let me look at the initial energy. So I'm looking at the energy of the extractor. And this is its initial spectrum. This initial spectrum, by the way, I want this process to terminate in a time shorter than this square root of n over c, to start and terminate it. Why? Because otherwise, somehow, these external parts of the wave function come here and will spoil that thing. But in order for a process to start and terminate in some finite time, if you do the Fourier transform, which is energy in this case, that would have long tails. So this one will have tails. So in principle, you say, it has a big energy that is able to give it to the photon. But it doesn't, because otherwise it would violate relativity. So you would expect that if this was the initial one, and if I'm only looking at the cases when the photon came out, then I would see exactly the same thing, but shifted down in energy. I don't know what the energy of the extractor is, but whenever the particle gained more, because the particle started from something between 0 and 1, and now went to alpha, so when the particle moved like this one should move down. In reality, it stays exactly as it is. So if I look at the energy distribution of the extractor in the cases when the photon went out, I find it didn't provide it energy. Okay, so here's a question. Is that a problem? Because here I'm talking only about the cases when the photon went out. But remember, we have our conservation law in quantum mechanics, which talks about the total distribution of the energy, not about some sub-selected instances, not about some special cases, but overall. Overall, I have to take into account also cases when the photon did not come out, because it was part of the superposition of being here. In those situations, the wave function that remained inside, you might expect it would have some lower energy. In such a way that if I look both of the cases when it went out and when it didn't go out, overall the distribution of the total energy remains unchanged. And it must be because this is a conservation law. The Schrödinger dynamics tells me that there is no other way. It will remain unchanged. However, in this individual case, when the photon came out, you ask what happened. And there it is not concerned in that case. So what do you do in this situation? Well, there are a few things. One of the things is say, look, I don't care, because all I care is that the statistical thing goes. And that goes, so I'm happy. You may even say, I'm not even allowed to ask that, although it is not clear who doesn't allow. As I said, that was a consequence, which people got used to think is the only way in which you have to say. There is nowhere written in quantum mechanics that that is the only question you can ask. Even if you think of the statistical thing, here is what happens. You ask, how the hell did it happen? Okay, I made this time an experiment. And I know I put here a photon with very, very small energy. You know, maybe an infrared photon. Suddenly it comes out with energy like a big atomic bomb. Okay, while the extractor didn't provide it. And you may say, well, yes, but perhaps there are other cases, other boxes in other laboratories where you did and the photon didn't come out. And if you would collect all of those, you find out that there is no problem statistically. But what does that mean? Is the fact that this one that came out with a large energy took this energy from the other photons that remain in the other boxes in the other labs, that perhaps those labs don't even exist at the moment. So even if you think of this statistical view, is not that is not really a satisfactory thing. Okay. Other people may say, look, you cannot even talk about the energy because this photon had an energy that was not perfectly well defined. It was a superposition of things. Yes, but in reality, every single thing is a superposition of energies. There are no absolute pure states. So if you wouldn't be allowed to talk about conservation unless you are in a well-defined state, then you will never be able to discuss about it. So we were concerned about this, but here it's an example. So how does this work with the other story that I said at the beginning? You see, here is something that I could do with this example that in general you think you cannot. Although, as I said, if I were to measure the energy, I would modify the experiment, but I can make absolutely sure I can measure that fact that the photon initially definitely did not have an energy higher than 1. And because I'm measuring a property, you know, I do a degenerate measurement, and I measure a property that is certain, I'm not modifying the experiment. So this is what this particular case showed, that it is possible to see. On the other hand, the distribution of the extractor did not change. So that's why in this situation is funny. Actually, the way in which the statistical one works is very interesting by itself. I will, if I have time, I will get back to that. By the way, how long do I still have? Not too much. In any case, so we showed an instance in which, although the statistical thing works, at an individual level, provable, it doesn't. Okay. So that was, we had these results, we didn't have a clean way of thinking of them, and to formulate them in, or you know, with what happens in individual cases and so on. Finally, a few years ago, we succeeded publishing. But nevertheless, it bothered us that we found an event or a situation in which probably the individual thing doesn't work. So then, thinking of it, it occurred to Yakir, and then we worked on it, that although all that I said here, it is absolutely true, there is a tiny loophole in, if you think of the physics itself. So here's the question. We started with this particular state psi. Okay? We started with this state psi of x, which had this interesting property. So the question is, how do I get the photon? How do I prepare the photon in this state? Okay. So imagine for simplicity that you have this box that is an empty box. You have a laser that will put the photon in it. So what happens? The moment the box is empty, the laser has some energy. The moment it puts a photon in it with some energy E, the laser will lose some energy. So this particular state, psi of x, psi, it is some superposition, as we saw, some superposition of k with some coefficients k and some energies. And this went from 0 up to n, and E is 0 was, say, 0, and En was 1, all those higher frequencies. So this is the state that we aimed for. However, every single time when I put some energy there, my laser that I have it on the desk will lose some energy. So what one would imagine that is happening is the following thing, that I start with my, say, this is the laser, state of the laser, and let me say the state of 0 for the particle, for the photon in the box. And this I want to evolve. And what I will get a sum of k from 0 to n, ck, this one, let me call phi minus ek and ek. So this is the laser and this is the photon. Namely, whenever the photon is prepared in ek, the laser lost that particular energy. Well, it is an entangled state. So it is not exactly the pure state that we wanted to start with. But I want to prepare this. How can I prepare such a state when I am entangled with this object? Well, I can do that if this phi is in energy very spread out and smooth. In that case, whenever but of a scale that's much larger than the largest energy that it will provide. So suppose that if it gave some energy, this went slightly down, but all these states would almost in all cases overlap on each other. Okay. Just to make sure that you are familiar with something like this, imagine that you had a 2-slit experiment. So here is this with 2 slits, a source, a screen, and then, the standard, an electron may come here and there, and here, depending on where it is, you have the interference pattern. But you say the electron went from here, hit this slit, and turning that way. So the momentum changed. So it must give this entire wall with the 2 slits a momentum in that direction. On the other hand, if it went on this way, it will give a kick in that direction. So it gets entangled with it. But if it is entangled, how comes that these 2 things still interfere? And then you see the game in that particular situation. You say, it must be the case that this wall here has a very large spread in momentum. If it has a very large spread in momentum, something like this occurs. So that means that all of these are almost identical. So I remain almost pure up to a tiny correction. But you ask, how do I know that this must be wide in momentum? Well, you know, because you would like this wall to be in a well-defined position. You see, if the position of it is slightly shifted, the interference pattern there is shifted. And at a certain moment, if the shift is larger than the size of the fringes, I will not see. So it cannot be in a state with well-defined momentum or well-defined energy, because then the position is not well known. So it cannot be a state, that is perfectly defined in momentum, so then even this shift will move it to something orthogonal. It is like that because in the conjugate variable, that is essentially what happens here. It acts as a frame of reference to this thing. Okay? That is the main issue. So let me come back here. Now we understand it's the same thing, but not in momentum, in energy of the laser. So we recognize that these things here, this particular state is almost pure because these are very, very wide. So the experiment goes as previously. We also see that the spectrum of the energy of the created photon is finite, exactly like before. That is how I arrange the preparation. What will come out, because the state is almost identical to this, and I can make it as close to this as I want, will be exactly the same thing. So sometimes I have the photon with very high energy. And now we ask, okay, so let me take a step back and look. If before doing my measurement, I measure in the box what energy does it have, and I find some particular energy, Ek, and I look what happened with the laser, I see that the laser is shifted down with Ek. And I can check for every single energy here is shifted down. Now, interesting, although these states are almost identical, something is very important as far as conservation is concerned. Their average energy, by how much it's shifted, is shifted by that, by Ek. Even if the entire disturbance in the wave function is small, but the change in the energy is the same. That doesn't go away. So you see here that it only lost energies up to 1. Exactly as you imagined when you prepared it. But now you say, I'm not interested in the experiment in which I prepare it and I measure the energy immediately, but I want to post-select the fact that it came out of the box. Okay. So I want to make a post-selection on this thing, only to look at that type of energy. Well, what you find in that particular situation, if you post-select this on only finding the photon in that region around small x, you would need to act with a projector on this thing. Only look at a subset. So you will modify the interference coefficients here. How much? Well, let's see how much you will do that. And I want to make a connection with something that you will know. Here I said that this is the way in which I prepare it. I took that from 0 and I put it in. Let me rephrase it mathematically in a different way. Suppose that I start with this state already as an initial state. Okay, suppose I start with that state psi here. And suppose I start with my laser in this state phi. Okay. And later I interact with, so suppose mathematically I want to do this thing, the laser, and times the state, sum over n, Cn of Ck, from 0 to n, Ek. And then I went to this state, sum over k, from 0 to n, Ck, phi that lost the energy Ek, and Ek there. It's a different thing, but mathematically I arrive to the same place. So you see here, I can interpret the laser as a measuring device that told me what the energy of the photon is. So it is like a measurement that occurs. But it is a weak measurement because this one, which is the pointer, the energy of this is the pointer, I have to see how it went down. That was very undefined. So now I am in an example that I know. I start with psi. I make here a post selection that I am around x equals 0, and I measure weakly the energy with this. Okay. And I have to find what is the weak value of the energy in that state, given the fact that I find it around x equals 0. And obviously, around x equals 0, I will find this very high energy. So that means that if I look at what happened with all the superposition of different shifted states of the measuring device, given the fact that I find this around 0, it will indicate that value, the local value. So it means that the preparer lost a much bigger energy. So I see now that there is no non-conservation in that particular instance, as we thought before. The measuring device didn't give it, but the object that prepared it did. Which is very strange, because if I wanted to look at the beginning, I see that it never gives it. So somehow there is another non-conservation there. The two of them compensate. And it's a non-conservation, let's say, this entire phenomena, I will not be able to see it at the beginning, only after I perform the post-selection to see whether the photon came out. Okay. All right. So the final thing, you say, look, I understand now. If I really need to select to prepare this state, then it is the preparer that gave me the energy. But what if the state started in this pure state, as it is? Then there is no preparer, you don't need to talk about it, forget it, and then you are back at the fact that there is no explanation, and in this particular instance, things are not concerned. So our claim is that that state simply does not exist as a pure state. And the reason why not, remember, this is what we describe, this is some function, psi of x. But what is that x? Is not some absolute position in the universe. That is relative to a frame of reference. And the preparer is exactly a frame of reference, exactly like in this case that I erased it here, this wall with two slits. is a frame of reference for that location of the interference pattern. So if I would go and look at the entire, say, cosmological problem and with frames of reference, with everything, then I will always find that this preparer exists in the background. And just this particular, well, a function like this doesn't really make sense. Why don't we see in general the preparer? Because the statistical conservation doesn't require. That is the interesting thing. Only if I want to see what happens case by case, I had to go. The preparer basically almost doesn't disturb anything. Like in the case with the two slit, if I make it heavier and heavier, the spreading momentum will be bigger. I make it more precise, located in space, and so on. So the state of the electron remains pure. And I can look at this wall with the two slits just like a potential that prepares. So it doesn't disturb the problem at all if I just look at how the phenomenology goes. But if I want to understand the conservation, there is essential because, as I said, the shift from here to here is exactly like the shift from here to here. Is exactly the same shift, although it's difficult to observe, but it is exactly the same loss of conserved quantity, and that is enough to repair the case. So we looked only in this particular extreme situation, but our conjecture is that if you would really go and at all the situation, you would find that actually the conservation goes in every single individual case, and not only statistical. But okay, that is still a conjecture. Thank you.
So I have a question for you, Sandu.
Yes. Oh,
This is John. Sorry, by the way, I got sick over the holidays, so I apologize. I wanted to be in this week, but about a year ago, Andrew Jordan and Achim Kempf came to me and said, basically, can you put a signal, like a super oscillating signal, into a resonant device and see how it behaves? So Achim Kempf said, let's just consider, for example, a water molecule. A water molecule is resonant with electromagnetic radiation, for example, say at 6 gigahertz, but let's put in say 100 megahertz sort of base waves that have these super oscillating terms that reach up to the resonant frequencies of the molecule. And we'll just at these very localized regions, we'll create these super oscillating frequencies. And so rather than put it into a water molecule, we put it into an RLC circuit. And we put an RLC circuit right on resonance, and we said, well, let's put in the super oscillating signal at its base frequencies, but the super oscillating term is exactly on resonance with the RLC circuit. And the super oscillation, as you might have guessed, went right through the RLC circuit as if it didn't exist. But what you're basically pointing out is that in order to do this, and this is where my question comes for you, is I would need to take the time interval at which it is resonant and just chop it off in that time, chop the two ends off, and then say, how does that interact with the RLC circuit? And here's the question that I have for you regarding Achim Kempf. this is basically like saying, well, if I put it into a water molecule that has a very high decoherence rate, does it sample the superoscillating signal locally? Or does it does it take the entire spectrum of the superoscillating signal, which is going to be band limited, and process the entire thing? Or is it going to actually look at the local fast oscillation independently because it has a rapid decoherence rate?
So, okay. I'm not sure I understood it completely, but let me try to focus on one aspect. So here it is. It depends. This entire process with the box said, I want to open the box and close the box before the other parts of the wave function will come in, so that I will see that it is not this high frequency. So from that point of view, suppose that you want to illuminate a system that has two levels at this particular high energy, and you just send light which has very, very small frequencies. So you would expect, knowing that you do not have high frequencies there, that you will not excite the molecule. So what happens if I send now this particular wave, which I can arrange, for example, a super oscillatory region to be at the beginning and then the correction. Here in my case, I had two sides in the middle. So at the beginning it comes and it will excite it, but then comes the back of the wave packet and drags it down. Okay, that is what will happen. So if you look for times that are limited at the time when the super oscillatory part goes over, there is no mystery here. The molecule doesn't react on what it sees at that time. That is the electric field oscillating there. That is what it does. So from that point of view, while that thing lasts, and depending on how you do, it may last years and years, in principle. Of course, I'm not an experimentalist. So then it looks like really a very, very high frequency. Only when the correction comes in, you start seeing that things evolve in a different way. And if you wait on that long scale, then you will see the spectrum. So that is how it will work. Did this answer somehow?
Yeah, so basically what you're saying is the molecule would only see things locally in time.
Indeed.
And that basically assumes that the decoherence rate is fast compared to the dynamics of your super oscillator of your wave.
But it will. I'm not absolutely sure about that part, but you can just imagine that you have a monochromatic wave at that high intensity, at that high frequency. Later, you have to see exactly how happens so that the back of that wave packet corrects things.
Okay.
I would basically think more of the details of the thing that you are asking.
Okay. Okay, I'll let someone else ask another question.
I'll be happy to continue discussing. Yes. So
and
I
how
don't
long
have.
Are you here? When do you leave?
So probably in 2 hours.
Oh, you do.
Well, okay. It's the end of 2 weeks. Yes.
Okay. Sorry.
Yeah. But
thanks, Sandu.
I will come again. Yes.
Okay.
Any other questions beyond here?
I think Lev is preparing to ask from my body language.
Sandu, can you repeat the main kind of message? Because in the middle you said that there is no real problem, but it looks strange. So and then there is a. I'm not sure I understood exactly the claim that there is no psi of.
Okay. Okay. So here is the message.
Yeah.
We have number one. We have the statistical view about what is the what are conservation laws, which means that I have a system and the initial distribution is the same as the final distribution of the conserved quantity.
If you want, if
Yes.
you may I ask about this.
Okay, so this is the standard view.
No, but I think the standard view that if you start with eigenstate, you remain with an eigenstate. And
But
from
that is part of it. No,
Well,
that is no. The standard view is that if you start in a superposition,
so
you
then
will remain in a superposition with exactly the same probabilities.
but
That is the standard thing. It does not refer only to the eigenstate, which will be unphysical because you can never prepare precisely an eigenstate.
But again, everything is some approximation, but there is a fact that if you go as close to eigenstate, it remains eigenstate.
Yes, you remain an eigenstate. That's not a problem, but it is more. Schrödinger equation tells you, and this is, generally people mix two or three things. Some of them, I heard statements like the average will not change. Of course, the average will not change. If it is in an eigenstate, it remains in the eigenstate, which is obvious and it's a triviality. But the general behavior of the conservation law is you start with something having a given distribution of this thing, and the distribution remains unchanged.
But
the eigenstate is a particular example of this when the distribution is a delta function.
but can I start with the law, the eigenstate doesn't change, and then the proof that expectation will not change and distribution will not change?
No, because, well, look, what do you mean to start with that? If you run your Schrödinger equation,
Yes.
then obviously you don't need more than, you know how to solve the time evolution if you know how to, if the eigenstates are. So
Correct.
obviously that is a result that comes from this.
But also,
with what do you, but the question is, what will you see in practice? And in practice, you will see that if you start with a given state that has a distribution, the distribution remains unchanged.
but can you have an example when eigenstate go to eigenstate and probability does not go to probability?
No.
So
No, it's, look, they go from one to another, but you may want to ask, first of all, experimentally, what does that mean? And you want to ask sophisticated things. I start here with something that remains in this region, but there something that it could be scattered on. And before you find quantum mechanics, you want to say, how can I check this? I'm an experimentalist. I want to know. Now, if I start and I say, I measure here the momentum, then the momentum is there and the particle will scatter. This new experiment will be different because will involve an interaction.
Okay.
So if you want to see experimentally, it is not immediate what happens. Obviously, quantum mechanics tells you it's because I look at a quantity that I know it commutes with Hamiltonian, there's nothing else I should do. The distribution remains unchanged. But
okay.
my point is going beyond that. So once we accept that this is the basic thing, The question is it conserved in individual cases? That view doesn't tell you anything about individual cases. And if I would have not inquired following this example, if it didn't worry me, this strange example where the particle comes out and what we wrote in our first paper, there I see that at this individual level, before I consider the preparer, there is no conservation. I could have abandoned there and say, oh, it's a curiosity, and obviously it's not conserved. It didn't have to be conserved if that would have not worried me. But then when we looked, we found out that in fact the situation is more subtle. We have to bring a new element into the game. And once we do that, we found more. We found not only that over the entire ensemble it is conserved, but on the sub-ensembles, which the original one doesn't say about sub-ensembles. That is the novelty here.
You want to say that you cannot really, this is kind of strange. You admit that there is a distribution of some quantity. And then you see that this distribution remain all the same all the time, never mind what. So if you can measure it, so of course it's not a distribution anymore. You found a value. So you can say
I'm not
measure it.
I'm not measuring it. Look.
So then measure it. Will you change it?
I'm looking what happens on a sub-ensemble. The sub-ensemble does not have the same distribution as the entire ensemble. And it doesn't need to have. And I was looking at the sub-ensemble, and nevertheless, I can tell you that on this sub-ensemble of the cases where the photon went out, that remains unchanged. It is the same as in the initial.
So this is not
the sub-ensemble.
This is not a general statement.
This is an example. This is an example.
The general.
Look here. First of all, I find a situation that I believe it is pretty general. There is no proof at the moment that is general, but it opens the way of looking. At the beginning, we found this thing that had an obvious problem. It came out with completely different spectrum and nothing happened to the opener. So on that sub-ensemble, it was obviously not conserved. And looking into it more carefully, we found that actually there is something that could explain. If I would have not asked that question, I would have never found out that I really need to take a preparer into account, because just in order to look at the statistical distribution, that preparer is irrelevant. So you would have never found that. Now that we found that, in a particular case, we may want to find out whether this is a general property or it is only limited to particular cases. So it is still open. But it is a breakthrough from that point of view.
So you say that sometimes the preparer has this particular state in some cases, yes? Sometimes I bring you a box with a photon inside. In this, I prepare the psi of x with a box, and you say that because I can open it and maybe you'll find it, that there are some cases, I didn't open it yet, I didn't do anything. In some cases, there is a special preparation of preparer. Now, if you will never open it, it will never happen. Or what you say?
That's not what I say. Look, again, it reminds me the joke of people that, go from an airplane and see some cows and say, there are some black cows here. And the mathematician said, no, there are all kinds of stages. No, there are some cows black on the back. Okay, so I showed you an example where just by thinking that there exists, that just by insisting with the intuition that I need to have conservation in every individual case, we discovered something interesting. We discovered that we need to take the preparer into account, which was not needed for the statistical distribution. Nobody would have looked at that unless you asked about the individual cases. And you find, yes, there I understand it works. Is that general? I don't know at the moment. Do I believe it is general? Yes, I believe. Do I know what I need to do in order to prove? Yes, I have a pretty good idea, but it is still complicated. So it is work in progress.
So one last comment, why I'm skeptical. If you consider sigma x equal 100, okay?
Yes.
So I can prepare a very large ensemble of spins in a particular direction. Then I'll make a weak measurement, trying to find out that weak value equal 100 on a large ensemble. And I don't do post-selection yet. I look on my weak measuring devices. And it happened to be that they show sigma x weak equal 100. Now,
Yes.
well, I can then say that maybe there is something special in this case. And then I know, not it's really because I have in the future this, I can decide what I will do. If I will measure in Z, then sigma x equal 100 might happen. But if I will measure or whatever in X, but if I will measure in Z, it must be an error, a statistical error.
So here is something interesting. What I didn't discuss in detail is the fact that, remember, here at the beginning, I look at what happens with the preparer and what energies it transfers. If I really only measure, if I measure immediately the energy of the photon in the box, I see that the preparer never gave me anything more.
Yes, yeah.
On the other hand, if I post-select here, I found that it gave. So it is a very interesting thing. This entire phenomena did not end until I've performed a measurement of energy on my system. So it is, if you want, it is something delocalized in time. We only are able to see what happens to this by the time the event has finished. It is a very subtle thing, and it relies on the point that you are asking. If I will not do that, this will not appear. So it is a very intricate way in which conservation laws work. That is the thing. So, but you see, and it's interesting, where is the energy? Because it never enters into the photon. It's basically transferred from here to the, at the output photon, not at the photon in the box. It is very, very subtle. It is as if the preparer knows what will be done. That is the actual mechanism. So I think that this is, we are just starting to see a very, very intricate situation, and conservation laws are obviously highly non-trivial.
Okay.
Okay.
Sandu, I think you had a question.
Yes.
Yes, so when you gave the analogy with the two-slit experiment,
Yes.
talked about how this wall has to be spread in momentum because it has to be fixed in position.
Yes.
I was wondering what would be the corresponding constraint on the preparer here, because it has to be
Oh, here, no, here, yes. So here, you see, if I look at this state here, this is a superposition of different energies. Okay. Now, I want to look how this particular state looks in position representation. Yes. So in position representation, this state, as I told you, looks something like that, with a much higher distribution there. But this is not an energy eigenstate, it's a superposition. So it means it will evolve. Okay, so even though at the initial time it looks like this, you will see this, this part will start evolving, will wash out that thing, it will change. So if you want to sample it to see this high frequency, your measuring device or your extractor, the one that takes it out from the box, has to come at this time. That also corresponds with what John asked. You do the interaction, but you want to see these super oscillations. But for that, you have to do when the super oscillation exists, and that exists for a given time. The same way the preparer has to be synchronized, has to prepare it precisely at the same time. Now, if the preparer needs to put this photon in the box in this state at the initial time, the Fourier transform, you do the Fourier transform from time to energy, that has to be very large in energy. And similarly, the same thing for the measuring device, because the constraint is measure them at a limited time. Okay, that is essential. Yes, Kai.
So the eigenstates EK, those are states that fill this entire box, some uniform sine wave.
Yes.
When you do the measurement, you're getting out these localized packets that don't have extent, or they have tails, I think is what you said. So you're
No. What I get out, I get packages with no tails in space. I chop them.
okay.
In energy, we'll have tails because the thing that comes out of the box, if you look here, I open the box and I close it. It will come out like a monochromatic wave, but chopped.
Yeah.
So if you have something that is a finite wave train, is zero here, zero there. It is like this high frequency put dressed on a sink. That is.
So the question I'm getting to actually is that when you get that thing out, that's not one of the eigenstates of your original energy basis. So it seems like what you're doing is measuring a different energy.
No, it doesn't really matter. You look what the energy is. It is an eigenstate of my entire thing, which is the free space here, the box, and whatever. And it is not an energy eigenstate because I chopped it. However, it would be, if I look in the spectrum, here's how the spectrum looks. So if I look, the original spectrum of energies here, with this one, were all kinds of things here up to 1. Okay, so this is the probability and as a function of energy and nothing else. What happens after I open the box? What happens after I open the box and close? Well, sometimes something will arrive here at alpha, but not really an energy eigenstate. It would be something like a Gaussian that is picked. How picked is around this thing? Okay. That depends on how many oscillations I have there.
And also the cutoff, right?
There's no cutoff.
No, I mean,
chop.
it's truncated, which
It's
means
truncated.
that if you expand it into the original basis, you'll have to have something.
I will have tails. I will have tails, but the question is how wide this is. The width here depends on And it's easy to calculate because this is a monochromatic wave multiplied by a top hat function. So it will have like a sink. So it is here, I can make it narrow. Obviously, we'll have some tails. Let me make it, it will be very small in amplitude here. Yes, because the probability that it was in this region is small. And I will have here other things that come from the cases when it was left in the box. But if you look at this distribution, might be slightly reduced versus that one.
So it's a question I'm trying to get to here, which is that when I do this measurement with the opener, there's a set of outcome states I can get. Some are the ones where the particle is still in the box, and there's the one where it escapes.
Yes.
So I have a complete eigenbasis of outcomes I can get when I do this measurement with the opener. And that list of eigenstates is different than the energy eigenstates I started with. So it seems like what's happening here is that I'm making a measurement in a different basis. Than
No, absolutely not. This is a box in your lab. And you look at the energy of everything from there and outside. That's not really a problem.
I'm not saying it's a problem. I'm saying that a way to think about what's happening here.
It's not a different basis because also the space you should have included in your original problem. However, you can do, if that is the thing that worries you, you can do other things.
It's not that it worries me, it's that when I make a measurement in a basis, I get an eigenstate of that basis. And it's the state I get here is not an eigenstate of the original energy basis.
The original energy basis also includes states outside.
Yeah, but it doesn't include this truncated state, the one that you've cut off.
I'm not telling you that it's an energy eigenstate.
No, it's some eigenstate of whatever the measurement operator is. It doesn't have to be energy.
No, it's not an energy eigenstate of the of that thing. I'm not making an ideal measurement. Okay, the measurement has two stages. Stage one is the release. The release comes this. Then if you want, you can measure with an operator measuring its energy everywhere you find this. Okay, that is the thing.
So the analog would be, I don't do the opener, I just open the box and look at the original photons with my global measurements. And then because I want to cut the part of super oscillations. No, I'm talking about the analog where I don't do the opener at all. I just want to I want to see the eigenstates that I prepared in the first place.
Sure. Then, because you know that is zero outside, you don't need to check anything outside. It's enough for you to check. But once you get this idea, then you realize that you can simplify it mathematically and get something much, much simpler. So, for example, instead of releasing it, you could say that you put two partitions here. You plug them in the box, and you only look whether you find it there. Or, instead of energy, you may look, for example, at a particle on a circle. Okay, and I prepare it in states of angular momentum, of low angular momentum, but which are such that in this region, they oscillate very fast. And then, I don't know, it's different amplitude there. So if I were to look at this region of space, I will see much higher components of angular momentum. So now I'm only looking in this particular set of eigenstates of angular momentum into the IM phi. My opener is simply I project on that region, and then I look the projection on that region, I expand it into the IM phi, and I will find a component into the I some very big number M phi, which is much bigger than all of them. And then it's everything contained here just in eigenstates of angular momentum on the side.
Sandu, I have to make a comment that it's
Yeah.
very appropriate that your talk on cutoffs and post selections in time is not being cut off and post selected in time because somebody else needs the room. So
Good.
Let's give Sandu a thank you very, very much.
In fact, that is much simpler to do, and that's what we did in the second. It's technical, I think.